Hi, this is Jim, W6LG for Ham Radio Basics. Welcome to my radio room classroom here on Wolf Mountain. These 10 videos are a review of all of the 462 questions that make up the general license question pool. The idea behind the videos is a way to prepare for the exam. I'm going to be reading the question and then the correct answer, and when I can, I'll provide a brief explanation as to why that happens to be the correct answer. So here we go. This is part 5. Okay, G5A01. What is impedance? And the answer is C. It's the opposition to the flow of current in an AC circuit. So it is sort of like resistance, but it can be complex. So it's the opposition or resistance to flow of current in an AC circuit. G5A02. What is reactance? And reactance is the opposition to flow of alternating current caused by capacitance or inductance. So you've heard the expression capacitive reactance and inductive reactance. Both of those oppose the flow of alternating current. When we looked at dipole antennas, we discussed briefly capacitive reactance, and inductive reactance. Which of the following causes opposition to the flow of alternating current in an inductor? And the answer is reactance. So it's which of the following causes opposition to the flow of alternating current in an inductor? It's reactance. G5A04. Which of the following causes opposition to flow of alternating current in a capacitor? Same answer, reactance. Capacitive reactance, inductive reactance. G5A05. How does an inductor react to AC? As the frequency of the applied AC increases, as the frequency of the signal increases, the reactance increases. G5A06. How does a capacitor react to AC? It's A. As the frequency of the applied AC increases, the reactance with a capacitor decreases. They work in opposition to each other, so it's a little bit confusing, but as the frequency of the signal increases with capacitor reactance, the reactance decreases as it goes up in frequency. G5A07. What happens when the impedance of an electrical load is equal to the output impedance of the power source, assuming both impedances are resistive? So we're talking about a situation where the output impedance of the power source is equal to the impedance of could be an antenna. So the answer there is the source can deliver maximum power to the load. This is when things work the best, when it matches. In this case, the electric load is equal to the output impedance of the power source. Could be a transmitter coupling to an antenna, and the antenna is purely resistive. There's no reactance. It's right at that line. It's neither above or below. G5A08. Why is impedance matching important? Think of antennas again, and that's so it can deliver the power to the antenna. So it's A, so the source, the transmitter, can deliver a maximum power to the load, the antenna. G5A09. What unit is used to measure reactance? It's in ohms. So it is could be G5A09. What unit is used to measure reactance? What's the unit of measure for reactance? To measure, so it's B ohm. These others make no sense anyway. So G5A10, what is the unit? What unit is used to measure impedance? And again, it's B ohm. G5A11, which of the following describes one method of impedance matching between two AC circuits? Which of the following describes one method of impedance matching between two AC circuits? And that would be, you put an LC network. Think of a matching network could be like an antenna tuner between the two circuits to match the impedances. So there'd be inductance and capacitance. G5A12. What is one reason to use an impedance matching transformer? The answer is the reason why you use a matching transformer is to transfer power. So it's B, to maximize the transfer of power. It has nothing to do with ripple or radiation resistance. A good example of this might be an impedance matching transformer at an antenna. The antenna might be, let's say, 200 ohms, and the feed line is 50 ohms, so you use a 4-to-1 matching transformer. G5A13, which of the following devices can be used for impedance matching at radio frequencies? Well, we already talked about a transformer working. We know that transmitters have many of them have pi networks in them. We also know the length of a transmission line can affect how things match. So the answer is D, all the above, really. G5B01, what dB change represents a 2 times increase or decrease in power? 2 times. We know that 2 times is 3 dB, so it's B, approximately 3 dB. G5B02, how does the total current relate? How does the total current relate to the individual currents in each branch of a purely resistive parallel circuit? And the answer is it equals the sum of the currents through each branch. This is a confusing question. Basically, it's saying it's a purely resistive load, purely resistive parallel circuit. How does the total current, how does that equal, or what does it equal in terms of the parallel circuit? And it's C, it's the sum or the addition of the currents through each branch. So if you had 1 amp going through one branch, and let's see, they're parallel, 3 amps going through the other, it would be the total or the sum. G5B03, how many watts of electrical power are used if 400 volts DC is supplied to an 800 ohm load? Okay, so I'm going to put up a dialog box. We know from the past that E equals IR. We don't know the current, so let's see if we can solve for the current. So we've got 400 equals the unknown current times 800. So if we divide 400 by 800, the current then equals I equals half an amp. So I equals 0.5. Okay, so now we know pretty much all the variables. So if we wanted to do power, the other word that I use is pi. P equals IE. Power equals voltage times current. We know that we have 0.5 amps flowing and the hit the wrong key, and the voltage is 400 volts, and that equals 200. So there's the answer, B, 200. G5B04, how many watts of electrical power are used by a 12 volt DC light bulb drawing 0.2 amps? So if I can bring up a text box again, we've got, so we're solving for watts. We've got current, we've got voltage, and we know that one of the basic formulas is pi, and we don't know what P is. We know the current is 0.2 amps times 12 volts, and that equals 2.4, and that's answer A, 2.4 watts. G5B05, how many watts are dissipated when a current of 7 milliamps flows through a 1250 ohm resistor? So we're looking for watts, and we know that power equals voltage times current. Current times voltage is the way I put it up. What we don't know here is what the voltage is, and the voltage equals current times resistance. So we've got 7 milliamps times 1250 ohms equals, what did I do with my calculator? There it is. Okay, so we've got 0.007 times 1250 equals 8.75. 8.75 volts. So now we know the voltage, so power equals, the current was 7 milliamps times 8.75 volts equals, looks like it's going to be 61 something. Calculator again. So we've got 0.007 times 8.75. I did that wrong. 0.007 times 8.75 is 0.061. So the answer is A, 61 milliamps once we move the decimal over. All right, so we solved for the voltage, and then once we got the voltage, multiply that times the current. That gave us roughly 61 milliamps. Had to keep track of where the decimal place went to. All right, let's go down the page here. 6. What is the output PEP from a transmitter if an oscilloscope measures 200 volts peak to peak across a 50 ohm dummy load connected to the output? This question is really deceptive because a lot goes on here, and I got it wrong and I had to go look. Frankly, I don't even know why this question's on there, but P equals IE. And the real question here is, what's the voltage? Now we know it. And you get misled because you think, okay, it's asking for peak to peak, and you're looking for peak envelope power. But as it turns out, you have to take the voltage, let's see if I can do this, and you take it for half its cycle. So we're going to divide that in half. So it's really 100. Then we're going to multiply that times the RMS value. So it's going to be times point, has it 0.07, I put that in wrong, 0707, which equals, instead of it being, so we've gone from 200 volts to an answer of 70 volts. 7, if I type it right. Again, what they're doing is you look at the sine wave, there's a bunch of math involved. You're going to take just as it goes positive, and then you're going to take the root mean square. And that throws me because we're looking for PEP output. In any case, so we know that the voltage is roughly 70 volts. And we know it's a 50 ohm load. So we could do it a couple different ways. One is to take the voltage squared divided by 50 ohms. Let's see if that works. It may or may not. Well, we start with P equals IE. We know the voltage. We haven't solved for the current yet, but we can also do with a little bit of math. P equals a voltage, squared. So we've got 70. This is a hard question, and I don't know what needs to be on there. I'd rather see a question about operating than the one like this that's just so convoluted in its math. Divided by, so it's the voltage squared divided by 50. And I have no clue as to what the answer is going to be. So let's see. Calculator, maybe I've done it wrong. So we got 70.7 times 70.7 equals divided by 50 equals, well, I got the right answer. I have no great idea why. So we've got 100 watts. This is one of those questions that you may never be involved with. It's, I don't know. So it's the trick in this one is that 200 volts isn't 200 volts. It's half that times root mean squared. And then you do the math. So it's 100 watts. G5B07, what value of an AC signal produces the same power dissipation in a resistor as a DC voltage of the same value? Well, this is going back to this other question. We're back to root mean squared, RMS. Well, I guess we're lucky they removed that one. What is the RMS voltage of a sine wave with a value of 17? So 17 times 0.07 is going to be 12 volts. So it's B. G5B10, what percentage of power loss would result from a transmission line of line loss of 1 dB? We know that 3 dB would have been half. 1 dB is about 20%, and that's C. That's a good one to memorize, by the way, is memorize what 1, 2, and 3 dB do. G5B11, what is the ratio of peak-to-peak envelope power to an average power? Okay, this is a tricky question. What is the ratio of peak to average unmodulated carrier? Well, there is no peak, so it's 1. That's just meant to fool us. G5B12, what would be the RMS voltage across a 50 ohm dummy load dissipating 1200 watts? So we know that we're looking for RMS voltage. So we've got 50 ohm dummy load, 1200 watts. Let's do some math here real quick. We're dealing with watts, so we're not talking about peak-to-peak voltage. So we've got 1200. Oops, 1200 divided by 4.9 equals 244 watts, 0.9 I think it was. So the answer is B, 245. So it was, we solved P equals I squared R. The current ended up being 4.9 divided into 1200 volts, gave us the 245. All right, on to the next one. Okay, G5B13. What is the output PEP of an unmodulated carrier if an average reading wattmeter connected to the transmitter indicates 1060 watts? Well, again, it's a tricky question because unmodulated would be just a steady state carrier, so it's B, 1060 watts. All right, this one I played with earlier, and I had trouble getting the right answer, so let's see if I can do it. G5B14, what is the output PEP from a transmitter if an oscilloscope measures 500 volts peak to peak across a 50 ohm resistive load? And again, I don't know why these questions are on here, but P equals IE. And we've got to determine what the voltage is, and that's where this gets tricky. So it's 500 volts, and we divide it in half because we want to take just half the cycle. So we've got 250 volts to work with times root mean squared, so times 0.707, and that equals some number. So let's see what that is. So we've got 250 volts times 0.707 equals 176 volts, 176.75. All right, so that's really the voltage that we've got to work with. So we've got P, again, P equals 176.75. We don't know the current. Crap. Retype that. We do know that power equals I squared R, or we can do the voltage squared. So it'll be 176.176. Boy, I'm having a tough time typing. 5 times 176.75. So the voltage squared divided by the resistance of 50 ohms. So let's see what that mess works out to. So we've got, time for the calculator again, 176. Uh-oh. What did I do? Okay, so we've got 176 times 176 equals, really? Divided by 50. All right, so the answer is B, and it is. Again, this is a question I think is there just to give us some trouble. So it's taking half the peak-to-peak voltage and then multiplying that times the RMS, and then taking that squared divided by the resistance, and that gets us to 620 some odd watts. Not an easy question. All right. G5C01. What causes a voltage to appear across the secondary winding of a transformer when an AC voltage source is connected to its primary? Okay, we're talking about coils of wire adjacent to each other, so it's mutual inductance. G5C02, what happens if you reverse the primary and secondary voltages of a 4-to-1 voltage step down? Well, it would step up. So it becomes, secondary voltage becomes 4 times the primary. I don't know why it's, you could read this a couple times and really not understand what they're saying here, but the secondary voltage becomes 4 times. This is a step down, this is a step up. G5C03, which of the following components should be added to an existing resistor to increase the resistance? Well, you'd add a resistor, B. G5C04, what is the total resistance from 3 100 ohm resistors in parallel? Well, it would be that divided by 3, so 33 ohms. G5C05, if 3 equal value resistors in series produce 450 ohms, what is the value of each? Well, it would be 150 ohms. Each one adds. G5C06, what is the RMS voltage across a 500 turn secondary in a transformer with a 250 turn primary connected to 120 volts? Okay, so we've got to figure out the turns ratio. It's about, let's see, the secondary is 500, so it steps down. It's roughly ballpark 4-to-1. It's going to be 26. So we've got 2250 divided by 500 equals, I'm going to cheat again with a calculator. I'm too tired to figure this out. So it's 2250 divided by 500 equals about, okay, 4.5 turns. Let's get that out of the way. So we've got, the answer is 4.5 turns. No, the keyboard doesn't want to work. So we got 4.5 turns, and all right, so we got 120 volts divided by 4.5 equals the 26 volts. Okay, G5C07, what is the turns ratio of a transformer to match audio? 600 ohms to 4 ohms. So we're going to go, let's see, what was the turns ratio? All right, this one's a bit tricky. So we've got 600 divided by 4 equals, that would be 150, right? So we've got 150. Now it's the square of the square, so it is the square root of 150. Which is 12.2. All right, so it's A. If you have, think of this way, if you have let's say you have a turns ratio of 3-to-1 for real easy numbers, the impedance transformation is the square of the number of turns. So it's 3 squared, which is 9. So you have a 9-to-1 impedance transformation. So it's not the turns ratio, it's the square of the turns ratio, which is why I had to take the square root of that turns ratio of 150 to 1. Again, a bit of a tricky question. And one that most guys won't get right, by the way. G5C08, what is the equivalent capacitance of 2 5 nanofarad capacitors and one 750 picofarad connected in parallel? All right, so we've got 10 nanofarads and move the decimal over 3, so it's 10.75. The answer is D. 10 here, 0.75 there. G5C09, what is the capacitance of 300 microfarad capacitors connected in series? So it would be one third of that, or 33 microfarads. They're opposite the resistors, so if they were resistors, they would be added. G5C10, what is the inductance of 3 10 millihenry inductors connected in parallel? So it would be a third of that, 3.3 millihenries. G5C11, what is the inductance of a 20 millihenry inductor in series with a 50? So when you have something like this, it's going to be, before you even do the math, it's going to be less than this lower value. I'm sorry, the inductance connected in series. So these are like a resistor. You've got 50 and 20, 70 millihenries. G5C12, what is the capacitance of a 20 microfarad capacitor connected in series with a 50? All right, in this case, it's going to be 14. And I can tell you without even doing the math, because it's always going to be less than this lower value. And in this, you can toss that one, and that one, leaving us with 14. G5C13, which of the following components should be added to a capacitor to increase its capacitance? Well, another capacitor in parallel. Parallel they add, series they divide. G5C14, which of the following components should be added to an inductor to increase the inductance? You do those like resistors, so it would be in series. G5C15, what is the total resistance of a 10 ohm, 20 ohm, 50 ohm connected in parallel? Well, it's going to be less than the 10. And that leaves us with 5.9. That one's way too small. These are crazy high. That's not in the ballpark, I think. That's if you added these together, which would be the wrong answer. So it's a 5.9. G5C16, what is the conductor? Why is the conductor of a primary transformer winding of many voltage step trend larger diameter than the secondary? The primary is large to handle a current. So when we talk about wire sizes and why the conductors are larger, it's going to be current. So it's to accommodate the higher current. G5C17, what is the value of in nanofarads? What is the value in nanofarads of a 22,000 picofarad? All right, so we're going to move the decimal place over 3. So 1, 2, 3. So it's going to be 22. It's C. G5C18, what is the value in microfarads of a 4,700 nanofarad capacitor? Well, again, we're going to move the decimal place over 1, 2, 3, so 4.7 microfarads, D.